So I think most of you just came from a class. Is that correct? You were just sitting in a class. So I hope you've had enough of an intermission or a break to be ready for another class. Okay. So I've had very patient listeners today. Jose Luis listened to my Spanish during lunch. And so I told him that I would be very patient with your English. So that's another way of saying I would be delighted if you would interrupt me and ask me questions, because it makes the whole evening a lot more interesting than me just going on for 90 minutes, correct? So I first need to know, have you ever been dealing with the load side of the electric grid? Have you ever looked at where electricity goes? Yes or no? Yes, you have. Okay. And what type of loads did you look at in detail? Did you consider how electricity is actually being used? Or did you always, as electrical engineering students, think about how we make it and then somehow it's being used? Any volunteers? Okay, we'll warm up over the course of the evening. So I'm here to give two seminars, one tonight and one on May 11th, which is 4 weeks from now about. And my background is in the building sides of things. And I'll tell you a few words about buildings in a second, because I thought it might be helpful for you to get better understanding of how energy is used in buildings and what opportunities we have to improve this. So I stop here right now and I'm asking, do you fundamentally follow my English? Is this understandable to you? Yeah? Or am I too low, too loud? I can adjust all these things. Perfect. Okay, good. So use this as an opportunity to practice your English. This is a small crowd. It's growing, but it's still a small crowd. So I would suggest maybe if we could possibly dim the first row of lights. I think that would improve the contrast. Será la luz. Oh, perfect. So, yeah, it's a large room. It's a relatively small screen, so I will use this little pointer to hopefully point out the things that are important. So, I'm here with while I do have a European background in education, I've been spending a lot of time in the United States, and I've been teaching there for a long time. So I come here with a bit of a US-centric perspective of the energy problem. So I have a few metrics that are, of course, based on numbers from the United States. So buildings are typically divided into two buckets: the residential building, which is your home, the piso, the apartment, or the standalone residence that you live in. And it's much more common in the United States that people, even of average income, can afford a home, a standalone single-family home. And apartment living isn't quite as popular. In cities, yes. In New York City, that's all you find is apartments. So you have the residential buildings, and then you have commercial and and institutional buildings, C and I. Or we could just call them commercial buildings. And commercial buildings would include this building, would include an airport, would include a hospital, a school, right? All these things are commercial and institutional. So we have residential and commercial buildings. And today, I'd like to give you an insight into the opportunities for building to grid integration from the perspective of commercial buildings. And on May 11th, I will have a focus on residential buildings, okay? So we start big and we become smaller next time around. And of course, I hope that next time around I have a class or an audience at least the size that I have tonight. I'm very pleased to have as many students here today. So let me begin. And some of the numbers I'll show you now will actually will include both residential and commercial buildings. So we have about 120 million buildings in the United States, okay? And of the primary, of the primary energy, they're responsible for 42%. There are three energy sectors: buildings, industry, and transportation. And the other two sectors necessarily cannot make up for more than 58%. So obviously buildings makes for the single largest market, right? If you ask yourself where electricity goes, it's 72% of electricity goes into buildings and 34% of natural gas. Does anyone know how the primary energy breakdown is in Spain? In the three sectors, buildings, industry, and transport? Do you know those?
I read it on the number, the percentage.
Oh, 30? Do you think 30 buildings and the others 30? So about even among? Does anyone know? I don't know. It's a real question.
Yeah, actually 27 buildings. 31, but I have the figures here. 27 buildings, right? Which is 17% residential and 10% services, I mean hospital and the like.
Yep.
31 industry and 39, almost 40% transportation.
So it's quite different, right? So you can see from 27 to 42%. Okay, so you can see that it's a big load, right? It's a big demand. If you look at the total energy consumption of the United States building block, or building stock, excuse me, so that is all of those 120 million buildings together. In terms of this wonderfully arcane unit that you might see again, BTU is called British Thermal Unit. Don't ask me what it means. I could explain it to you, but I would need a few more hours. It's still used in the United States. Every English person in the United States says this is no longer used in Britain. We should not call it British Thermal Unit anymore. But consider these units of energy, terawatt hours, for example. But this ranking alone should give you an indication that U.S. buildings consume more energy than all of Russia, all of Japan, and all these other countries, just short of China and the United States' total energy consumption. So I hope, and of course, this is 42% of that, right? That's the total fraction, okay? So there's an interesting thing about buildings, which is if you look at the number of buildings, which is these circles, there are very many small buildings. And the building size here is in another arcane unit called square foot. It's about the size of my foot squared, which means you can pack about 10 of those into square meters. So take these numbers and divide them by 10, you're pretty close. So these are buildings being 100 to 500 square meters in size. These are 500 to 1,000, and so forth. So we have a lot of, we have 25,000 small commercial buildings. These are all commercial buildings. And the bigger the buildings become, the fewer we have. And the really big buildings, we have very few of. Yeah, does it make sense? So if you fly into Chicago, you see those few large buildings, right? And the total floor space, interestingly enough, is about even in those categories, which means the few large buildings are really big, right? These are the skyscrapers. And that's why this blue bar is about as high as the other ones, even though we have very few of those buildings. So a very diverse market with a diversity in size and a diversity in contribution to the energy. But what we can observe is that the energy consumption has been continuously rising since, well, the 1950s. And you can see that the growth in energy consumption, and we stop about 42 BTU out of about 100 BTU, right? That's why we have 42% of total energy consumption. And you can see that building size, or the size in square feet, has grown linearly along with that. Total building square footage and the energy consumption. They seem to go hand in hand, is what this chart says. And does this seem like it's going to stop anytime soon? No. In fact, the predictions are that if we go forward another 40 years, relative to the 42 quadrillion BTUs, we have to expect another 30% increase. And why is that? Well, more buildings are being built, and even if they become more efficient, we still tend to build more. One thing that's very different between the commercial and the residential building world is the way energy is used. In commercial buildings, we have a lot of energy spent on lighting. And that's because commercial buildings tend to be compact and tend to have only a small area of the building that sees the outside. So the opportunity for daylighting is reduced. So we have a lot of lighting energy consumption, a quarter of the pie, followed by space cooling. And what I will talk about today, we'll look at the space cooling wedge. It will look at potentially the space heating wedge, definitely the ventilation. And so you can think of about a third about a third of that pie is what I'm going to address today. I'm not going to look at changes to our lighting system or water heating or things of that nature. How does it look differently in residential buildings? Residential buildings are really dominated by heating rather than cooling. Does anyone have an idea why that may be the case? You see, it's almost odd, right? We're talking about buildings in the same country, but one really needs a lot of energy for cooling, the other one for heating. Anyone have an idea? And by the way, the pie sizes are about half-half. So if 42% is the total U.S. energy consumption, residential and commercial buildings each contribute about half to that, right? So any ideas? What's so different about these two types of buildings?
Maybe the residential consumption, there are people who are using this energy, and the way that people use energy are not as efficient that a commercial.
Oh, so you think it's an efficient? Here you have humans acting things on and off, and maybe less efficient than automatic controls in big buildings. Okay, that's play a role because we do control automatic control here, but other things. Any other ideas? What could be different? Remember what I said about lighting? The buildings tend to have very little outside, so they're driven by the internal load. So you have lots of lighting and people, and what does that do? It generates heat, right? So they seem to need much more cooling. In fact, we have a lot of buildings that need cooling year-round, even in cold climates. It's very odd, right? And that's because the core of the building needs to have the heat removed. You have a lot of computers running, lighting on, people using their little personal devices. All these things consume energy, and all this energy is turned into heat, right? So essentially, you can have buildings that 80% of the floor area is constantly needing cooling, even though it's minus 10 degrees Celsius outside. It's very strange, but that's the way it is. So that's why these breakdowns are a little different. So on May 11th, I'm going to talk about some other opportunities in this sector. But today, we're going to look at the commercial building world. So we're back to SI units, which is good. And we're looking at energy intensity in kilowatt hours per square meter in year along this axis, and the total consumption in total country consumption. So you can see, well, again, I'm trying to make this interactive, maybe with an unexpected volunteer. What's the difference between office and healthcare? Healthcare is hospitals. Andreas. Or any other volunteer. So offices, in terms of intensity, in the middle of the pack, right? They're not as, they don't have quite as low of an intensity as a vacant office, which is not a surprise. When it's vacant, there's no energy consumed. But, and not as high as healthcare. But why is it out here in total consumption? Why is office here and healthcare here, right? It's like twice as much for office.
Maybe there are more offices than healthcare.
There's just that many more offices out there. Exactly. So what I'm talking about today applies here and applies here. So I should be pointing to this here. It's the office, the education. So this is what we call commercial and institutional market. It would be, healthcare too, warehouses. Why are churches over here? There are lots of churches, right? For example, in Sevilla. But no, and even in the United States, we have lots of churches. But they're basically vacant 6 days out of the week, right? That's why their total consumption is here, right? Make sense? Okay, so you get to see that we can have very different energy intensities. And are you comfortable with the term energy intensity? The consumption per square meter of area every year. Is something that you feel comfortable with? Good, okay. And so now we have to get a little technical, just a little bit, which is to show you a building with its envelope. So this is what you see from the outside. It's a skyscraper, it's a school, it's the building we're in right now. This is the mass of the building, and inside you have zones on the perimeter, and I think there's a window, right? So this is why this would be called a perimeter zone. It's on the outside of the building. And a core zone, a core zone is one that doesn't have a connection to the outside. So think about the floor plan of a building. You can say, well, approximately 5 meters around the perimeter, that's the perimeter space, and the rest is core zone. And that's the area that requires a lot of cooling. So these two types of zone, they are typically conditioned with, what are we using? Ice cubes? Chocolate, ice cream? How do we make people comfortable in Sevilla in August, in this building? Anyone who smiles is going to be asked a question. No, I'm just kidding. So,
Comfortable temperature.
yeah, how do we do that? We roll in ice cream for everyone?
We use the air conditioning.
Yeah, air conditioning, exactly. So it's these things up here, right? So we circulate air, okay? And so that's what you see here. You can see air being distributed to these zones. They're the same thing. And what do we do with the air? We return it. This is what's happening here. We return the air. We don't throw it all away, because if we want to have 24 degrees Celsius in here in the summer, we might deliver air at about, let's say, 20, and we return the air at 24. We are not ejecting that air to the 42-degree Sevilla afternoon environment. No, we're recirculating this, and that's happening right here. So we're mixing this return air with some outside air, and this is where most of the cooling occurs. So we cool the air, and then we distribute it. And sometimes we need to reheat, which is happening when this air is a little too cold. It's just right for this, but too cold for this, so we have to reheat. Not that important. So we use cold air, about 16 degrees Celsius, normally the supply air temperature. There's a cooling coil. The cooling coil is basically, looks like if you have a car, you open the front of your car, or under the hood, you look for your cooler, right? The cooler of the engine. It's copper tubes with aluminum fins on them. And through it runs cold water. And how do we cool the water? Well, we need a device called a chiller. Chillers in big buildings are possibly the size of this room. They're very big, and they're single most expensive piece of equipment in a building, okay? And these chillers use a vapor compression cycle just like your fridge or your air conditioner, like this one, but they are much, much bigger, and they remove the heat from here, and then they eject it, or basically reject the heat to this cooling tower, okay? So take the heat from the spaces that comes from people, lights, and plug loads, things people plug in, extract the heat and remove it. And you can see, and I point to you now to the biggest energy consumers in buildings, apart from light, but it's this compressor here. This compressor can be hundreds of kilowatts. Yeah, it can be megawatt size in large buildings. These pumps are everywhere, and I forgot one. Any ideas which one's very important too? That one. Those distribution fans. Those fans, in fact, I had a tour this afternoon. You remember, Jose Luis, on the roof? We had lots of air handling units, and each of those have big fans. They consume a lot of energy. Okay, so I think that's to give you an impression that in order to keep buildings comfortable, especially in the cooling case, we need a lot of technology, a lot of systems to operate. So this is to show you a large office building. And here we have such a chiller. And obviously this is a little bit of an older drawing, but it holds true by and large. You have these pumps, you have the chiller. The chilled water is sent here to an air handling unit. You don't ever see air handling units. They never win any design prizes. You don't ever see an Apple logo on them. They're pretty ugly. They're hidden away. But they exist. They keep this building comfortable. And so you have these cooling coils. You have a fan. It distributes the air, and it comes to these VAV units. And I don't want to point to anyone here, but this is one. There's one. All of these. And then in the end, we return the air and condition the air here again. Okay, so this is what we see. We see big variable air volume systems. Most buildings are conditioned by changing the amount of air and keeping the temperature constant. So when it's very hot, a lot of air comes in here. When it's not so hot, it's less air, but the temperature stays constant. That's called VAV, variable air volume, all over the world. Okay? Now, in retail buildings, in stores, so I will use the word retail today. A retail building is your Mercadona. Where do you like to shop? Give me some big shops. Lidl. What else do you have here in Spain? Carrefour. Yeah, Carrefour, for example. So a lot of these buildings, they use these interesting rooftop units, also called RTU, just to abbreviate rooftop unit. And these rooftop units typically serve specific zones. So this building has 3 rooftop units, and you might, for example, have an electronic sales area down here with lots of televisions and game stations. And back here you might be selling furniture, and so very different requirements here and here. And this might be an office, so that's why we would use different ones. And these rooftop units, they take outside air, they condition it, they send it in, they return it, and everything's in here. And what is in there, I'd like to briefly. So we take outside air and we we reject heat through this fan. We take fresh outside air in, and we mix it with return air, and then we supply it into the building, just as shown here, right? So there's a lot of stuff in that rooftop unit, but it's a pretty modular technology that you can put on a building, okay? That's commonly used in retail environments, okay? In environments that need a lot of cooling and air supply. And lastly, so we had large office buildings. Remember, have VAV systems. They have chillers. And we have retail buildings with rooftop units. We also have medium-sized buildings. And the technology doesn't look all that different from the big buildings. But in a medium office building here shown with 1, 2, 3, 4 stories, you have these packaged air handlers that sent down supply air at about 16 degrees Celsius throughout the building. That supply air comes out here, which is exactly what I pointed to you. And then the return air is collected, it's returned here and conditioned. And what consumes energy here are, of course, the fan, or let me just blow this up a little bit. It's the fan here, the supply fan, and you have this cooling coil here, which has a compressor. Now, these systems also vary the airflow, but there's one fundamental difference. Through the cooling coil here, you do not run water, but through that cooling coil, you run the refrigerant directly. And these systems are called direct expansion systems. They take R134A or R410, these refrigerants, they take them, they expand in the cooling coil, and then a compressor condenses that. A compressor compresses it, a condenser condenses it, and rejects the heat. So in smaller or medium-sized buildings, we have a lot of direct expansion technology. Okay, so this is a perfect time to ask, are you now completely comfortable with buildings? Más o menos, right? A little introduction. I want you to be feel comfortable with what I'm talking about. Okay, so at this point I would need to switch presentations. I think I do. F11. Okay. So, I'm going to now that you feel well prepared with a basic understanding of buildings, going to get into the technical meat of things, and I'm going to give you a presentation that needed 3 lines of a title, right? That can't be good, right? If you need 3 lines to introduce the topic, but it's not that bad. So the first thing is building portfolios. So building portfolios means I'm taking multiple buildings and considering them at the same time. I'm aggregating them together. I'm not looking at individual buildings, but I'm putting them together, okay? How am I putting them together? Am I actually moving the buildings? No. I'm just thinking of them as potentially being joined together, mathematically joined together, right? Because there may be a benefit to this, okay? And I'm going to consider these buildings in a way that is not commonly thought of. I'm going to ask, would it be possible that buildings actually do something that they don't normally do, which is to provide electric grid services? Okay? And the electric grid services we're going to consider today is buildings participating in day-ahead energy market, which is the Mercado Diario, right? Okay, and providing frequency regulation, which would be control de frecuencia. Okay, so there are 2 things up there. First of all, it's building portfolios, not one building at a time, but being put together. And it is buildings providing these services. And how they do this, I'll introduce to you in a second. The work I'm presenting here has been done over the last 5 years, together with my PhD student, Greg Pavlak. And he says hello. I spoke with him earlier. And so let me begin. Buildings. Worldwide, I talked about the US, 42%. We talked about Spain, 27%. Worldwide, it's 32%. So Spain is less than the average, and the United States is above the average. But it's still more than any other sector is used for, or buildings is requires more energy consumption than any other sector. And that's the International Energy Agency, IEA. The Energy Information Agency is an agency that is run by the Department of Energy. And the EIA is the source of a lot of really good information for us as researchers in the United States. It's actually a very powerful source of information for a lot of analysis. And they're predicting building energy demand to increase by 1.6% every year, right? Which doesn't sound like a whole lot, but we're today happy when we get 1% on our savings account, right? So 1% compounded each year is still quite a growth, right? And I don't know that the doubling rate is still significant. So we have a growing sector, and we have a significantly growing sector, faster than any others. And, well, what can we do about that? The Pacific Northwest National Laboratory in Washington is one of our largest national labs. They predict that we can save a significant amount of energy through improved control. And approximately 6% of the US commercial building consumption can be saved by better control. And at the same time, the National Renewable Energy Lab, it's another national lab, says that we can actually achieve 50% energy reduction in buildings by better design, holistic design, if we put things together. So we have a certain significant, in my eyes, opportunity for efficiency in buildings. And let's see how we can unlock that. Okay, so global electricity demand has been growing 2% every year. That's electricity, not energy, but electricity only. And that's more than any other final form of energy. The United States consumed 78 quads of fossil energy. We also consume 17 quads. These are quadrillion BTUs. I'm sorry for these units. And so we can see that the picture here is fossil. These are the total energy consumption, quadrillion BTU, petroleum, natural gas, coal. Nuclear is over here. And the renewables are those two stacks. And this non-hydro stack, you can see 4% of that is solar, wind 22. This one is growing very rapidly, and wind is too growing very rapidly. But nonetheless, we need to come up, we need to increase the rate of growth of renewable energy, and that is happening. In fact, California is predicting significant challenges with the rate of renewables growth that we're experiencing right now. Okay. So there's a transition that we are going to expect, a transition from the centrally provided, central generator kind of electricity distribution. We had predictable generation. However, the majority of the future renewables, like in Spain, will likely be wind and solar. Those two make scheduling resources difficult, as you know. And we might, through improper integration of variable generation, actually suffer quality issue problems, power flow imbalances, and in general grid stability issues. So what could be solutions to this change in our system, in our energy system, from a fully centralized fossil fuel dominated environment to one of highly distributed and highly renewable energy system? Well, one of them is we might need a lot of grid storage. So there's quite a bit of discussion going on in the US, how much the US actually needs scale storage. The other avenue is what we refer to as demand response, DR. And in demand response means the load side, the demand becomes responsive. It is no longer just requesting energy, but it's now listening, right? It's still a balance between supply and demand, but it's a change in which the loads now are willing to accept change, or are willing to change their patterns of consumption based on certain conditions. Does that make sense? So if it's really difficult to provide every joule of power at a particular time, well, maybe there are options on the load side to change our consumption behavior. And those we're looking at right now. And again, I'm quoting the National Renewable Energy Lab. They're saying demand response and load participation, so flexible loads, is going to be critical in achieving higher penetrations of renewable energy. So the National Renewable Energy Lab says, without demand response, without load flexibility, we're going to have a really hard time. Okay, I can skip that, right? Electric system overview. Okay, we talk about continuous balancing supply and demand. Typically, it's human activity and weather effects that dominate this diurnal profile that we are seeing here. So, for example, here to here. So what I heard today during lunch is that in Spain, we observe a daytime peak of about 40 gigawatts. Is that correct? And a nighttime low of about 20. So you have a peak to value ratio of 2 to 1 in Spain. I don't know what your load factor is, but these are the numbers over lunch. No one opened the book, but that's what we heard during lunchtime. It may be different, but so while the day-ahead energy market involves scheduling or unit commitment, right, of base load, load following peaking plans, we then create from that a time-dependent energy price. But that's not enough, because there are a lot of smaller effects we need to take care of, which is subsumed under frequency and voltage regulation or ancillary services provision. And so if you look at a snapshot, this time snapshot here, this is 7 to 10 a.m. These are 3 hours. You can see the need for regulation in megawatts from minus 30 to plus 60 megawatts. And you can see this is a pretty noisy signal. And over a few hours, 6 hours or so, this signal integrates to 0, or should integrate to 0 fairly quickly, but it's highly erratic. So this is, as we say, old hat to you, right? We know that. Move on is what you're thinking, correct? Yes, good. That's what I was hoping. That's where you say, yeah, we know that part. Okay, so ancillary services, I'm going to look particularly at frequency regulation today, okay? Okay, now what do I mean by building to grid integration? So this is kind of a term that you've heard Antonio refer to earlier. We have this workshop or this course in June, building to smart grid integration, so there's a little smart in here. But in general, building to grid integration, to me, if you asked me, I would tell you it means that the supply side and the demand side, at least when it comes to buildings, they talk. They're no longer, hey, give me 50 megawatts, and somehow they manage to give you 50 megawatts. It's a dialogue between, you know what, I'd like to have this much power right now, but I recognize there is a grid stress event coming up, or there is a generator coming offline, or there are other problems. And building to grid integration is fundamentally, to me, integrating the operation of buildings in a way that is responsive to the needs of the electric grid system. Okay? So, how can we do this? How can we adjust, change, alter our energy consumption behavior in buildings? I can turn up the lights, right? But that would be dangerous, looking at you. Sorry. Falling asleep, but we don't want that. No. We could do that, but we don't have to be quite as drastic. Remember I talked about buildings having all this around me here? Yeah. All this is thermal mass. I can use the thermal mass as a buffer to change the way I operate my HVAC system. Okay? And I could also optimize active thermal storage systems. Ice storage systems are popular to do that. But they don't have to be ice storage or chilled water storage systems in the building. I can use, basically I use building thermal mass as a kind of a flywheel, a thermal flywheel, to change my HVAC system operation. Now, I just used the word HVAC and I haven't even thought about it twice, but does everyone know that this means heating, ventilating, and air conditioning? No, but now you do. I should have told you beforehand. So this is all the building systems I introduced earlier, right? The fans, the motors, the chillers all together make HVAC. Okay, that's an acronym, an abbreviation you will hear again today. So this is something that I've been looking at for a long time, or longish time, 1 or 2 decades. But buildings can also potentially supply ancillary services, and some of the benefits of providing ancillary services through flexible loads includes increased system reliability. So if I have more people participating in the provision of reliability services or ancillary services, I might have a more reliable system. I manage my risk, right? I may have lower emissions, especially if the variation of power doesn't cost me anything. Market power mitigation means I now have a lot of people participating in the provision of an ancillary service, so I reduce the risk that one big company is taking control of the market. That's market power, right? So that's avoided. And I might increase my system efficiency. Okay, so I can operate buildings to buffer, or I can operate buildings to take advantage of the inherent thermal mass I have, or I can operate my buildings around ancillary services. In the first case, I'm particularly thinking about looking at day-ahead energy market and recognizing that we have substantial variability in energy prices in the United States between nighttime prices and daytime prices. So in Chicago, where we have operated a number of buildings this way, we've seen nighttime electricity prices of $5 a megawatt hour. We've had prices of $0 a megawatt hour. We had prices of minus $20 a megawatt hour. So people were paying you to please use energy, right? Does anyone know why these strange effects can occur? Any ideas? When would a power generating company tell you to pay you to use energy?
In the case of one generator couldn't stop the turbine, or for
Exactly.
example, nuclear generation.
Yep,
They
nuclear.
can stop the generation of energy. And if they have more energy that the energy that's demand, they need to sell it free or pay you only for have stability in the generation.
Yeah, exactly. So he's absolutely right. So there are times, mild times, especially we see this in the Midwest, the Chicago area, Ohio. We see where certain power plants, they cannot be turned off because they are needed the next day. So it's 3 o'clock in the morning, everyone's sleeping, no one's using a toaster or coffee machine, everyone's sleeping, but the next day we need the power plants to operate. So at that time, we have a particularly low demand, prices are low, and at times they're negative. And with wind, of course, things are not becoming easier, but on the contrary, more difficult. Okay, but let's take this strange situation out of the picture and say, in general, we have low price of generation at night and high price of generation during the day. And what if I could operate my building over the next day to take advantage of these lower nighttime prices and avoid the higher daytime or afternoon prices? Okay? And that is what this first aspect is about. It's managing the thermal storage and optimizing around that. But if I also want to do ancillary services, the question is, which one takes priority? And to answer the question, ancillary services or day-ahead market, we're going to co-optimize the participation in these energy and ancillary services market. And we're going to find strategies that are going to balance the two. Okay? Okay, so I told you that I'm going to speak about building portfolios. And the reason that we're taking a departure from an individual building to going to look at portfolios, because buildings are connected to the same grid, and they can be aggregated. And looking at one building at a time might actually be suboptimal, right? It may not be market optimal. So what we're doing is we're giving an optimizer. So we're going to talk about optimization. I know in this room there are lots of people that are interested in optimization, optimal power flow, optimal unit commitment, and all these things. But we're going to give an optimizer the information about all building characteristics available within a building. And we're allowing that optimizer to exploit, which is a technical term which means to take advantage of these characteristics to arrive at a perfect orchestration of a number of buildings. And this is what the idea of aggregation brings with it. I have individual participants, but I put something on top that knows about the underlying systems and comes up with an optimal strategy that considers all of the features at the same time. So the hypothesis that drives this research is that because the building characteristics are different, we say there is diversity among building characteristics and operation. These building characteristics and operations diversity creates opportunities. And these opportunities, we don't know how big they are, but we wanted to find out whether or not they are present. Okay, and that motivated this research. Okay, so a single slide on model predictive control. I mean, we could speak a while about this, but model predictive control is kind of an essential technology to this. It's something that electrical engineering students will encounter in their controls classes and maybe even use it. Who has been encountering that mode of control? Any controls classes here? Anyone? No controls classes? None? Okay, good. Well then, So what is MPC about? It's model predictive control. Okay. So it's it's the new iPhone 6 of controls. Everyone wants to do it. Everyone wants to have it. So what does it do? Okay. So it takes a model. So you have a process. You create a model, and then with the help of this model, you ask for you ask, what do you want to achieve? What do you want to minimize? And that optimization function you can minimize by solving an optimization problem. So I'm basically asking, I would like to minimize something over the next day, and I solve this optimization problem, which may take me a long time, but once I found the solution, I take the first step of that solution, and then I take that step. Okay? And I actually control the system to that new control. And then I again ask, okay, over the next 24 hours, I again want to minimize some objective function. For example, I want to minimize operating cost of my chemical plant. Okay? Let's say you are in a chemical plant making a chemical. And you say, okay, how should I operate over the next 24 hours that I minimize cost? And one of the sources of savings may be that the prices are different, or the weather is different, or some things change over time. So you're developing an optimal plan, an optimal strategy. And then of that optimal strategy, you just carry out the first step. You take that step, and you do the same thing again. So you're always pushing this time horizon in front of you, which is why this is called receding horizon optimal control, or receding horizon model predictive control. And you come up with a strategy. So you predict the external variables, you determine an optimal policy, and you just execute the first action, that one. And at this point, you repeat the problem. You determine optimal process by repeating those 3 steps. So this is what is fundamentally behind model predictive control. So model predictive control requires a model, right? And so we're going to talk about modeling a little bit today. And this moving horizon or receding horizon implementation is very common. And this horizon could be an hour, 2 hours, a day. It always depends on what you're controlling and what the dynamics are. When it comes to problems that have a diurnal cycle, that have somehow a night-day cycle, it makes sense to consider the next day, right? To look at the whole next 24 hours. Okay. So we need an explicit model. We have a high-level MPC and a low-level MPC version. That's unfortunately something I need to tell you about. So high-level MPC is an approach in which the strategy consists only of set points for the problem you're controlling for the planning horizon. Whereas low-level MPC actually adjusts the control's decisions every hour. It tells you, do this and then do that. So it's a little different, right? In one case, I need to plan every individual control action of the problem. In the other case, I say, well, these are the set points I want you to track. This is the reference strategy I want you to follow. And we're going to look at high-level MPC. Okay, I wanted to take that out, and I haven't, sorry. So I mentioned to you that we're going to look at buildings and 3 types of buildings. And the first one is the retail building, a store, which we said was Macedona or something of that type. So I'm going to tell you that it looks like this. It is a big box, and it has rooftop units on top. And these rooftop units take outside air. They run it through an economizer that decides on the right amount of outside air to bring in. They have a constant volume fan. They have a DX, remember that, a direct expansion cooling coil. They might have some gas heating if necessary. And then they have supply air. The air is then heated to the set point, 24 degrees, for example, and then returned. So here are some characteristics. It's an older building. It's 2,300 square meters in size. This is the air change rate. This means how often is the complete contents of the building turned over with outside air. And that's because people go in and out or windows are opening. That's what we call air change rate. An air change rate of 1 means every hour the complete contents of the building needs to be exchanged. These stores have very little windows, so glazing is 7%. Lighting power density is how many watts per square meter you have in lighting. This is equipment, so monitors and toasters and everything else that you plug in is equipment. And about 7 square meters for every person in the building. The HVAC system, heating, ventilating, air conditioning, is a constant volume, direct expansion rooftop unit. I showed you a picture of this in the beginning. Okay? The medium office building looks like this. See, it's quite a bit bigger. It's, well, how much bigger? It's 2,200. It's about 6 times the size. Okay? And you can see much lower air change rate. That's because fewer people go in and out. In the shop, people go in and out constantly. Much more glazing. 40% of the external area is glass. People want to be able to look in. And it's using a variable air volume system. I mentioned to you, it's a system that changes the amount of air. And we use a direct expansion cooling system, where refrigerant is expanded directly in the coil, then compressed, then condensed. And this picture looks almost similar. Here we have, however, a special system that is a dedicated outdoor air system, but we have a DX cooling, we have a variable air volume fan, and we serve the entire building. Lastly, we have a big building. That's a large office building, and 80,000, 100,000 square meters is not uncommon. These are buildings that we're dealing with. But remember the introduction I gave you. We have not very many of those, but they are very important, right? Okay, and those require chillers. They have a chilled water variable air volume system. So we have these big chillers that make chilled water. They need pumps on the condenser water side, on the chilled water side, cooling towers, and we have the cooling coil, and we have the big fan supplying air. I think we have a technical issue to contend. Good opportunity for me to take a break.
The channel with the screen is low.
Okay.
Probably when we exchange file.
Go ahead, please.
Probably because
No.
they are watching you.
Please, whatever it
Not
takes.
on the screen, you know,
It's
the other
just,
channel. But a way to solve this is just recording.
yeah, totally. You can all get up and stretch your legs, and I have the benefit. I'm allowed to walk around all the time. Can you still see from back here? Do you see enough? Can you see? Mira, is possible? Okay. No?
I'm using the phone with the presentation because it's from me so far.
I told you there are lots of empty seats up there.
Yeah,
So everyone who feels like they actually got a bad seat, please come up front. I would love to have your company. I feel lonely. There are like 10 seats here. I cannot increase the size of that pantalla, that screen. I eat first row. Free popcorn. So what level of students are you? Master students or bachelors? Or Grado, right? Yeah, okay. But all electrical engineering or industrial engineering with a focus on electrical, right? That's the one. Okay.
Have a background in heat transfer and thermal.
They do.
Yeah, but no, but
I took all that out.
no, but yeah, the introduction was very good because
Okay.
the acronyms and all those names in English,
Yeah.
I'm familiar with them.
Good. Okay, but you're all about to be finished when? When are you? When will you graduate? Is this your last year or first year or? Last year. Okay. Alejandro? ¿Puedo continuar? Gracias. Okay. This one here?
¿Esta pantalla, Antonio? ¿Ese mensaje de abajo? Ocultar, ¿le doy ocultar? Sí, ocultar.
Okay, so to the audience in the País Vasco and in Barcelona, in Malaga, I apologize if you missed the description of the models. I summarize, we have 3 building types. We have a retail building, a medium office building, and a large office building. And the large office building has systems that you would find in this building. Okay, so it's actually quite similar. Okay, now the model predictive control, as I mentioned to you, requires a model. Model predictive control involves continuous optimization. So what do you think that means for the model to be used? So let's say this. Every hour I need to send a new set point to the building. Right now it's 7 o'clock, roughly. It's 7 p.m. In an hour, I need to send another set point, and then another set point. And I need to do lots of optimizations. So what would you like the model to be that I need for the optimization? Remember, the model is required for the optimization. What is a characteristic you would like? Simple. Good. Simple, you're on the right track. Simple. Too simple, or?
No, it has to have the most important variable to know how the heating transfer is, how the building is going to
Behave. Yeah, perfect, yeah.
To behave.
Yeah.
And I don't know, you can, if the prediction is from 1 hour to 2 hours, you can have a not too simple model, but it's per minute or per 10 minutes, you need to have a simple model. So to calculate all the stuff, I think you are going to do that. It's difficult and
It takes time.
It takes time.
Yeah, exactly.
And to confirm something, you need to have some variables. I don't know. You have to do it
Perfect. Yeah.
step by step,
Yeah.
but not too fast. Because doing things fast and with a lot of uncertainty is not too good.
So I think you hit on a number of very good points. So we need a model that's good enough, not too simple, but simple enough so that I have a chance to calculate a new strategy every hour, right? Because if I need to send a new set point at 8 o'clock and I only have 45 minutes left, I cannot have a very complex model. And a lot of building simulation programs are extremely complex. And they would take every floor of this building and every window and every desk and model everything, all the heat transfer, the long wave radiation between my desk and that wall, and you can see that takes forever, right? So if you want a really exact program. And so what we've done is we've developed a simplified model that is based on equivalent resistance capacitor networks, RC networks. You use them on a daily basis, right? Correct? RC networks as electrical engineers you even use them during breakfast, lunch, and dinner, right? I mean, it's what you do. It's RC networks. There's a thermal equivalent to this, and we use RC networks too. And in fact, we have developed an RC network that tries to emulate these buildings, and we can model the heat transfer that's going on with interestingly enough, with a single zone model, which means the whole building is one big air cavity, one big room, but we need different types of RC models for the enclosure, for the walls. And so, for example, the retail building is that big box. Remember that flat box? And what I show here is the temperature history in the middle of the summer. So this is our 4,760 to 4,940. And you can see in the green circles, you can see the temperature of 24 degrees being held here. And in blue, you can see something which I call Energy Plus. Energy Plus is this very large, complex, and relatively slow energy simulation program, which is too slow for a lot of the optimal control problems. So we had to develop this simplified model. But what you can see in direct comparison, that there's excellent agreement, right? That's the cumulative temperature error here for an 11 parameter RC network. And this is the electricity consumption. And you can see the electricity consumption of that store. You can see some deviation, but it's minor, right? Blue is the exact model, and green is the simplified representation. So this is to say, well, we've got a validated model, okay? And we've done this for the medium off building too. And you can see on the weekend, this is a weekend effect. So you see 24 degrees, and this is a Saturday, shorter day, and then Sunday, that medium office is closed. No one goes to work on Sunday. People do work on Saturdays, unfortunately, sometimes. But in the store, every day is the same, right? The stores, at least in the United States, there's no Sunday when it comes to shopping. Shop all day. So which I don't, but people kind of are used to that. And so here you can see, again, pretty good agreement, but this is basically when the system is off. We say the building is floating, right? It's been cooled to 24 degrees. And so how does the exact model, the Energy Plus model, differ? And you can see small differences. I think what I want you to walk away with is that it's a pretty good agreement, good enough for a control model, okay? And then we do this for the large office building, and we, again, hopefully come to the agreement that both temperature and energy consumption and their deviations are very good, okay? So takeaway is we have a reduced order model, a simplified RC-based model that is almost as good as the detailed model, but much faster. But you can see the RC networks are 21 parameters, 5 parameters in one case, and 11. And we actually developed a system that looks at all kinds of RC network complexities and chooses the best one. Okay, so now the third section of multi-markets. I mentioned to you that it has been common to consider buildings providing, participating in the day-ahead market, mercado diario, right? So that means I look ahead and I basically anticipate I predict the pricing and the weather for tomorrow. And I know price is going to be high in the afternoon at 3 p.m. and it's going to be low at night. So I'm willing to spend more energy at night to pre-cool the building, a little colder, so that when you come in, the building's actually relatively cool. Today, I need less cooling. So I basically shifted load. It's called load shifting, right? I shift the load from the afternoon to the morning, nighttime hours. Okay. Let me say that in multi-market, the idea of participating in multiple markets is something that we do with traditional generation equipment all the time, right? I'm not sure if you've looked at the unit commitment of a range of generation systems, but basically we're solving dynamic programming or mixed interlinear programming problems all the time, which basically asks the question, when do we bring on the load following combined cycle power plant? When does the peaking gas cycle come on, and all these things, right? That's a common thing on the supply side. This kind of a multi-market optimization has been used in vehicles. The University of Delaware has asked the question, can we have electric vehicles that are charged at night, not automatically at highest rate, but in an intelligent way to participate in the electric market, okay? So the vehicle to grid charging was one. And then Peng Zhao is another PhD student of mine. We looked at frequency regulation provided by buildings but just frequency regulation. So what are some of the challenges of doing multi-market participation of buildings? One of them is we need to consider that people still need to be comfortable, right? And I noticed that you're all getting a little sleepy because the air is a little stuffy, right? So we need to make people happy. We cannot dim lights, visual comfort, indoor air quality needs to be considered. So we need to bring out enough inside air. And passive thermal storage is not the same as electric storage, right? Electric storage, like a battery, you charge and you discharge. But the dynamics of charging the building as a battery, if I may say so, so the dynamics of charging this wall with energy, cooling it down and letting it warm up is very different from an electric battery, right? Because I can take, let's say I can take all night to cool this wall. It's a nice thick wall, right? And I come in and I have a nice cool wall tomorrow morning at 8 o'clock. And then I say, you know what, I really need to suck out all the cooling, all the stored energy in 1 hour. Can I do this? No, I can't, because the heat transfer from here, it's natural convection heat transfer. It depends on the inside room temperatures. I can't control that. So it's very different, right? We need to consider that. And then HVAC systems have capacity constraints. They don't have infinite capacity to provide cooling, right? So what we're going to do, and I'm going to present today, is I'm going to present an approach in which I perturb the HVAC systems and look at the energy response of that. So that's what I call here the whole building energy model perturbation approach. So I perturb the model. I'm going to see how is it responding to changes in control. Okay? So here is the way we are going to do frequency regulation estimation. And because frequency regulation is such a long word, I'm going to call it FR. Are we good with that? FR? Good. So how are we going to do this? So imagine it's 1 o'clock in the afternoon, and you have a building that is being maintained at 23 degrees Celsius. Okay? And at 1 o'clock, so this is the hour from 12 to 1, or so for this hour, you're asking how much FR, frequency regulation, can I provide? The building cannot be colder than 22 and not warmer than 23.7. Okay? So I'm allowed to move in this range. So far, so good. And I've kept the building at 23 exactly. So now I'm here. What can I do? Well, I can start to cool the building, right? I basically say, okay, I'm going to take one step down. What's going to happen as I step from black to light blue? You have any building, any building, your fridge would behave the same way. You're walking up to your fridge and you're changing the set point. You're lowering the set point. What's happening? Yes? Pardon? Yeah, it would start to require more energy, right? And that light blue of set point reduction is found here. It's actually going to use a little bit more electricity, right? And then if you depress it further and further, the energy consumption will go up. Does that make sense? Promised. I know it's late. I know you want me to get through this, but you actually understand? Yeah, I know you do. So as you depress the set point, the consumption goes up, right? Yes? Good. Conversely, I could say 23 is cool. I'm going to float my set point up. I'm going to go from 23 to 23.5, 24, and so forth. You see those upward things. What's happening now? Simple extension of what we just discussed. I use less energy, right? Here, in cooling more, I need more energy. Cooling less, higher set points, I need less energy. So what have I achieved? I have achieved some load flexibility by simply adjusting the set point. Okay? Now, This is a building that has the fans operating at 50%, and it has a DX coil with 4 compressors. The first 2 are operating, the third one is cycling, and the fourth one is off. Okay? So you can see that that change in set point leads to that change in consumption. So if I go from here, this is 350 to 450, and this is, how much is this about? It's more than 550, right? So what let me ask it this way. Is this response, this is a symmetric increase and decrease in set point. Is the response of the system in terms of electricity symmetrical? It's not, right? And that's what you expect, right? If you have a fridge, and I'm sorry to use the fridge here, you have your beer in it, and it's all perfect and at equilibrium, and you're going to say, I want my beer colder, right? You're going to punch it from, I don't know what your beer temperature is, but let's say from 7 to 3 degrees Celsius, really cold, like, no, it's -2 in Spain, right? That's what they all advertise, -2, sorry. So from 5 to -2, so that has a pretty strong increase. But now I'm going from 5 symmetrically to +12. Why am I not getting a symmetrical response? Why is it different? What's different? Efficiency. What's happening as you increase your set point? You're actually, does the compressor run longer or shorter? The refrigeration cycle compressor.
The compressor start the machine start and then begin to consume the energy from the system.
Right.
And when they get the temperature, they stop.
They stop, right?
For a while and
Exactly.
start
So what if you add a temperature, let's say your beer is at 7 degrees. I try to make it a credible, practical problem. Fridge full of beer, 7 degrees. You set it to 12. What needs to happen for it to respond in terms of power consumption? It needs to warm up, right? And that takes time. It's just heat transfer, right? The fact that you need heat to rush in to reach that new set point, that's why it's not symmetrical. Okay, so if we have 2 compressors running and a third one cycling, that's this case here, we get this interesting relationship. As we increase the temperature set point, the power consumption goes down. As we reduce it, it goes up. And we might actually have to call for another compressor, for 1 compressor less. So this is 2 instead of 3. And here it's 4 instead of 3, right? This is a situation where you cool the building, that the 4th and last compressor needs to run as well. Yeah? And it's simply done by changing set points. So what I'd like you to understand is that if I can just set points down, I can make my building do some things that it would normally not do, because normally I would keep that set point flat and constant. In this scenario, I'm taking advantage of this temperature band, right? So I have some degree of freedom and I'm using that. Okay, so I have something like roughly plus minus 100 kilowatts in this building. This is a very realistic case. So this building can provide 100 kilowatts of frequency regulation up and down. We call it up and down regulation. What do you call it in Spanish? More or less the same. Arriba y abajo? Okay, good. So just so we're on the same page, right? Frequency regulation, what do I normally do to provide that? Jose Luis, what do I normally use to provide it? What do I normally use in Spain to provide frequency regulation? Generators, right? Big machines that you never see, but that they're expensive, right? So what do I use here? I use buildings that you see, that you use in a slightly different way. Does that make sense? Right? So instead of requiring big machines, I now change the way my load is operated. That's load flexibility. Now, are there potential problems? Do you see problems with this approach? So we just heard that ancillary services normally require separate generators that need to be bought. They're very expensive. They need to be operated. They typically use natural gas, right, in this case, or possibly combined cycle in some other cases. So a very expensive system. Why wouldn't everyone do this? I mean, I know I have good ideas, but why isn't everyone doing that?
First, you need to communicate with the grid. You know, you have
I need to communicate with whom? Say that again.
the grid.
With a grid? Okay. I need to get a signal, right?
You have to get a signal to know what temperature are you going to reach.
Mm-hmm.
Are you going to set?
Yeah, I mean, the grid doesn't need to know the room temperature in the building, but I need to tell the grid how much flexibility I have, right? So I need to basically tell how much I have. The other thing is maybe, this is better, maybe doing this all the time, 4 compressors, 3 compressors, 2 compressors all the time to provide frequency rating is something that can have a negative effect on your equipment, right? So it's something we need to consider. Okay. So if I provide frequency regulation from, let's say, 9 o'clock in the morning till 4 o'clock in the afternoon, this is how things could look. So I keep the overall set point low, and this is my regulation up, this is regulation down. And I told you that the temperature is asymmetrical, but the temperature bound is asymmetrical because I've changed the temperature bound such that the regulation is symmetrical. And I do this because this particular example is in a market. The PJM market is one of the big transmission organizations in America, is PJM. They require frequency regulation to be symmetric. Other markets have a separate up market and a separate down market. How is it in Spain? Is it one market or 2 markets? Do frequency providers have to do both? Both. So it has to be symmetric too. Okay, so this is actually the Spanish case. Okay, so you can see quite a bit of, and so what happens here is if you say that you have this much capacity for every hour, it's a different amount of capacity, you then go up and down potentially with your temperature. But you can see it's about 1 Kelvin in temperature, 1.5 Kelvin. It's not that much, right? It's not like you're freezing and frying people in 1 hour. Okay. So in the multi-market optimization, what we do is we solve an optimization problem in which we're trying to minimize a cost function which consists of the energy cost, the demand charge, and revenue for regulation. So here's where I can actually earn money. Does it make sense? So the energy cost is the energy used at every hour multiplied with the day-ahead energy price. Okay, so that could be a low price at night and a high price during the day. And I'll show you some examples in a second. And that over the planning horizon here of 24 hours, for example, that would be the energy cost. The demand penalty is a value that's defined by a threshold. So if the peak electricity consumption is below a target demand limit, this whole thing becomes 0. So only if I consume more electric demand, or if my maximum electric demand is higher than my target demand limit, will I have a demand charge, and I multiply that with a certain number of dollars per kilowatt. And the demand in the United States is typically dollars per kilowatt and month. So in Chicago we have $5 or $6 a kilowatt a month. In New York we pay $40 per kilowatt a month. Okay. So we have energy cost and demand, and then I subtract regulation revenue. Revenue means money generated or earned. And that is this change in power, that's this change in power that I showed you here, that I can provide, times the the regulation cost, or the cost or the price for regulation provision. Okay, and so that's the multi-market optimization that we're doing. So we want to find the minimum to that subject to some bounds on x, and x happens to be here the control variable, not the state variable, but the control variable. So in this multi-market optimization, I'm looking at a particular control variable, and for that control variable, I have a particular building peak demand, and then I'm going to take the control vector for the next 24 hours. So this is a vector of controls, and then I'm going to change and look at a number of perturbations to find out around that set point. So I want to point to this here. So I've got a set point strategy, that's x, and the deltas are around this baseline strategy. The baseline strategy I'm going to show you in a second will not be a constant. Okay, so here I'm going to look at a number of perturbations, and I'm going to then basically keep the one that minimizes this objective function. And the objective function is this one, where I'm also considering the regulation revenue. Okay, so let's look at some medium office results. So in the medium office, I'm now assuming this is midnight to midnight, and in this case, I have from 12 to 4 in the afternoon, I have what I call a, that's the demand period. So during that period, I'm applying a charge of $5.50 for every kilowatt over 325. And so what happens here is that if I'm trying to simply optimize around the day-ahead energy, and the day-ahead energy price is shown here on the bottom panel. So you can see the day-ahead energy price is between $20 or $30 a megawatt hour all the way up to about 75 or 80, right? So it's a factor of 3 between on-peak and off-peak. And the regulation energy is also shown in dollars per megawatt hour. And so you can see the regulation energy is actually quite valuable in certain hours, right? So this is when we expect a lot of need for regulation. Now, what you see here is the circles is what the building would do if it was just participating in the day-ahead market. It would pre-cool the building a little bit to take advantage of that. Now, if I combine day-ahead and frequency regulation, I get this black line plus the gray box around it. So these are the set points and the variations in temperature that I allow to provide a certain electric demand variation. So these gray hours are hours in which I take advantage of the day-ahead energy as well as take advantage of the frequency regulation pricing. So why don't I use any, if I jointly optimize both markets, why isn't anything happening here in this period? Well, the answer is during this period I have to deal with this target demand limit. I cannot exceed that limit over 325 kW. So if I wanted to provide some frequency regulation, I would have to keep the set point lower, like here, to go up and down. It has to be symmetric, remember, up and down. But if I keep the building colder, then I'm going to have a higher demand. So that necessarily means during this period, there is no chance I can provide both frequency regulation and still maintain the target demand limit. So this is when I have a low demand limit, and this is 325, and 325 is right here. So I'm basically telling the building, don't ever, during that red period, go above 325 kW. Okay. Now, if I, and so what this does is, or what the result of this is the same chart, is now we see the frequency regulation that we can provide is between plus minus 8 kW, that's pretty small, right, for a small, medium building, to plus minus 60 kW. On that day, we earned $12 in revenue from frequency regulation. It's not a whole lot, right? And our total savings, optimizing around price to optimizing around day ahead energy and optimizing around day ahead plus the frequency regulation, is an increase of about 1.5%. So not big, right? So it doesn't have a big impact. But that's because I've had a low demand limit to deal with during these hours. Okay, now if I raise that demand limit, meaning now all of a sudden demand is no longer a constraint, you can see that the combined optimization keeps a very low temperature. In fact, it keeps a low temperature throughout the day, and surprisingly enough, it keeps this optimized temperature set point, it's the same temperatures, always 23 degrees, surprisingly, and giving me a lot of flexibility for frequency regulation. And that has the benefit of, providing $56 in increased revenue. The savings go up from 2.3 to 15.7%. So huge increase in savings by participating in both markets. But I'm also consuming $23 more in energy and consuming 277 kilowatt hours more. So why do I consume more energy?
You need to have less temperature.
A lower temperature set
To
point.
have those.
To have that flexibility. Exactly. I need to have a lower temperature set point in order to be symmetrically able to go up and down. And the reason I can go up and down here is because I've taken away the 325 kW demand limit. I've taken off the lid. I allowed the building to do whatever it wants to do. So you can see economically I have significant savings, but it comes at an increase in energy consumption. Who normally consumes those 277 kilowatt hours? Who's normally responsible for that? The generators, right? Normally on the supply side, I have generators providing that. Okay, so I'm going to skip that because that's a little technical. Maybe I just want to say I can do more than just change my room temperature set point. I can also change my chilled water temperature set point and make the water I distribute throughout the building less and more cold, okay? But I will skip that at this point. Now, so far I've talked about multiple building types, and I've thus far looked at multiple markets. We've looked at the medium office building participating in the day ahead and the FR market, correct? So now I'm going to take multiple buildings. So how do I optimize multiple buildings? In order to do this, you have to imagine I'm now going to take each and every one as a building. So temporarily you have to think you're a building. And I'm going to be an omniscient, all-powerful optimizer who knows everything about you, and you tell me everything about you. And I'm going to find a solution that is recognizing the characteristics of each of you. And that's what I would consider a supervisory optimal strategy, okay? But I'm only going to look at 2 building types, not quite as many as here, but I'm going to start with 2. But nonetheless, what I have to do is I'm going to generalize the single building problem to the multi-building problem. And that involves every building, and let's say I have n buildings, can have its own optimization parameters. It can be in a different city, have different weather. It can have different utility signals. It can have a different model type. In fact, we have reduced order models and full simulation models that we can use. So you can imagine a diversity of buildings set up. Now, the multi-building optimization cost function is the same as we saw before. It's energy cost plus demand minus regulation revenue. But now the control vector is not for one building, but it's now for multiple buildings, okay? So B1 means building 1, and Bn is building n. And for every building, we can have different optimization schedules. So the flexibility is now at hand to optimize multiple buildings. And in each building, we can optimize, for example, room temperature set points or chilled water temperature, or other things, okay? And this is kind of how it works now. We have got this huge control vector, which basically says for every building and for each building and for each schedule, this is the control. And let's say we have one building, and the first building 1 has a reduced order model. It gets that part of the control vector. This reduced order model is also asked to consider frequency regulation. So this is the multi-market situation. So we have multiple buildings and multiple markets. And the second building is the same thing, also frequency regulation, but now we're using energy plus as the model. It's also possible. And this last building here doesn't have any frequency regulation, so we don't need that. So in case we have this optimal, we have the frequency regulation issue, we need to determine the optimal frequency regulation at the same time as we optimize the day-ahead energy. We put all these together, we get our regulation revenue, our demand energy cost. Once we have an optimal strategy, we then have, for each of the buildings, an optimal strategy, right? So this is a situation in which I am the perfect conductor. Think of a concert, Beethoven's Fifth Symphony, or the Sixth, even better. And you're all playing well together. I tell you all what to do. This is the kind of supervisory control, okay? That is supposed to tell us whether there is a potential. Now, this, I just wanted to give you a heads up because it's 7:30 about. No, it's, 7:45. Mm-hmm. Okay, 10 minutes. And that's what I wanted to tell you. No more than 10 minutes. So in this scenario, I now have multiple buildings. And imagine you have a large office building, which I call L, and I have 120 retail buildings, and I put them together in a portfolio. And why 120 stores? Well, I have 120 stores because they tend to, or they happen to have the same load-reducing capability as one large office building. And I put them together, and if I put them together, this is the total demand. And during those hours, from 12 to 4 again, that's when I observe my target demand limit. That's why I showed this white block here. If I pre-cooled all of the buildings in the portfolio, I could get down to this minimum line here. This is at the lowest I could pre-cool. And if I don't do anything, then I would have this upper value. This upper value is the standard control where I don't do any pre-cooling or change to the control, and I call that night setup control, NSU. And so this is a magnified version of this, right? I basically take this. So what I say is if the maximum reduction target demand limit is down here and the NSU is up here. So I arbitrarily to the midpoint here, a value of 19,432 kilowatts to be that value that I set my target demand limit at. And I'm looking at 3 scenarios, A, B, and C. In scenario A, I'm going A, B, and C. In scenario A, I'm basically telling the individual buildings, when considered individually, I'm asking only the retail buildings to provide the load reduction from this value to that. In case C, I'm expecting the office building to provide the total demand reduction. And in the case B, I basically ask them to share that. So this you can see here, right? In A, it's the retail building that needs to provide that reduction. And in case C, it's the office building that's supposed to provide the reduction. You can see that index P is portfolio. When put together, it doesn't change. So from a portfolio perspective, I would like them to achieve the same value of 19,432. But the question is, before they are put together in a portfolio, what are they asked to do? And if I start here with scenario and I'm looking at the retail buildings, if I look at the retail buildings as by themselves, individually, I am forcing each of them to provide a lot of pre-cooling. So you can see the temperature set point is depressed very strongly, and that's done in order to achieve a little bit of power reduction. And why is that happening? Well, it's because in the single case, before I aggregate them to a portfolio, the retail buildings are now charged with pre-cooling as much as they can. Okay? Now, if I put them together into a portfolio, then this temperature is chosen, which is the same as the standard in circles. So if I have a portfolio perspective, it seems like the individual retail buildings aren't doing any pre-cooling, any load reduction. And that's because they're not very good at it. So now I go to the office building. The office building is providing some pre-cooling just by itself. That's this green line, more than normally would happen. This is the normal building operation in terms of set. If taken by itself, it would cool down to this value. In the portfolio, the office building would sharply pre-cool more. Why is the office building doing more in the portfolio case? Well, because it knows the retail buildings are not very good at it. That's why it's doing more. And in this scenario, you can see that, let me look at this and come to an end here. These are the energy consumptions for the large office building and for the retail buildings. This is 120 retail buildings and 120 office buildings under standard operation and under optimized operation. You can see if we don't optimize them as a portfolio, we're using more energy because we're driving the retail buildings to do something that they're not very good at. And if we are putting the buildings together, I'm actually able to achieve about the same energy consumption. And relative to the individual case, I'm achieving great savings through the portfolio consideration. So I have 2 exclamation marks here because I want to point out that if I optimize them together, and I've beforehand asked all the retail buildings to do the load shedding, then the portfolio optimization gives me a large benefit. What that means is if I could come up with an optimization system that stood above everything, it can actually recognize that I have an opportunity to operate the whole better than the individual buildings by themselves. And we did start a little later, but you've been super patient, and I think I'd better stop at this point. Right? That's it. I got the hint that this is, yep, we have a few minutes to 8 o'clock. So I hope to have given you, in summary, a few things today. I've given you a bit of a background on what goes on in buildings, what kind of systems are in there. I talked about air handlers and chillers, all these things. Talked about the fact that buildings can participate in day-ahead energy markets, right, by recognizing low nighttime prices and higher daytime prices. Talked about the fact that buildings could provide in frequency regulation markets separately. Talked about the fact that we could do this at the same time, frequency regulation and day-ahead energy markets, and do this quite efficiently, right? And in the United States, that's actually possible. The Federal Electric Regulatory Commission now allows loads to provide ancillary services, FERC Order 745 and 55. And then I told you lastly that I can potentially put buildings together as portfolios. And if I look at them from that mountaintop perspective, and I know what the characteristics are, I can actually bring these buildings together and operate them in a way that is superior to the way that I would operate them individually. So at this point, we're going to ask ourselves in my group, how can we take this into reality and into practice? And so the idea is, how do we assemble those portfolios? How do we put them together? Should we take 3 schools and 1 hospital, or 1 office, 1 hospital, and 2 schools, right? So how do we build the portfolio? Portfolio construction is what we're looking at right now. And then the question is, how do we do this practically, right? How do we aggregate buildings practically at the same time? We need models, we need communication pathway, we need to send information to and from buildings. So these are some of the highlights that we're working on right now. So it being 5 minutes to 8, I know this was a 2-hour session. I wanted to maybe give you a chance to ask a few questions, and I'd like to open to that at this point. Yeah, please.
I want to ask 1 second, because the other party cannot hear you without microphone.
I need to.
No. You have a wireless microphone. That's the problem. When you were asking students for those who are only they will not.
Okay.
My question is, who is going to do this portfolio? I mean, for example, if they are public buildings, maybe the government can control this, but if they are a supermarket or 100 supermarket, like this case, who can do that? Who will do that?
Excellent question. So the question is, if you owned a hospital or a store, let's say you owned Mercadona, and all of a sudden, or I don't know, Stradivari or whatever the stores are, all of a sudden people control your set points for you. No, that would only happen if there's a good reason for you to do this. And the reason for you to do this is in the cost function. It's the fact that the regulation revenue is subtracted from your energy costs, right? It's an opportunity to reduce your bill and to actually provide a revenue to your building. So think of it this way. You would participate in that voluntarily. Let's say you own the Mercadona store around the corner. Let's assume there is one. And you are interested in maximizing your profit in your store, right? You have people to pay for and product to pay for, and you have energy expenses, and you'd like to keep your energy expenses low. Now, someone comes to you and says, you have a store that could be very useful for the electric grid system, and it could be useful if you allowed me to change your temperature set points a little bit, and at the end of the month, I'm going to write you a check for 5,000 euros. Would you want to do that? That's the situation. So it's voluntary, right? It's not something where I can say, give me your building and I'm going to control it. It's something where you say, 5,000, 60,000 euros a year, that's a lot of money. That's like 2 people that I can hire more. Yeah, I'm going to do that. That's the situation. And then who is it going to do that? It's likely going to be an institution that I call an aggregator, a company, a special company that aggregates these things together. Good question. Thank you.
Any other question?
For the case of the multi-building, there are many customers.
Yeah, for the case, no, I have a Pedro, I repeat. So for the case of the multi-building scenario?
Case of the multi-building scenario,
yeah.
There are many customers. Are you sure that all the customers are going to have benefit? Or maybe some customers are going to lose money and others are going to, because you optimize the global.
Yeah. So it's an excellent question. So if I put many buildings together, can I guarantee that the community global situation also means that everyone's individually will be having a benefit from that? I think what this would likely require is a situation in which the total benefit is for the portfolio is calculated, and then the expense of building operation without participation is calculated, and so everyone gets a certain fraction of the benefit achieved. It's not necessarily easy, but let's say there are 10 buildings, and each building is operated differently because they can, right? They have different characteristics. But let's say the portfolio as a whole saves 100,000 euros, right? And then they, what you would, over the total, and then you would basically make sure that these 100,000 euros are translated into 10,000 euros benefit for each of the participants. But it's a question that we are dealing with right now.
And regarding the real energy that each building is going to,
it's going to use,
to
right?
use,
to consume, yeah.
So it's like an equality benefit.
I don't have a perfect answer because you are correct. If we put the buildings in a portfolio, we're going to operate them differently than they would by themselves. So they're going to possibly use more energy and have higher costs on an energy basis. So the energy cost for me may be a little higher, but the revenue from, but I may have an opportunity to create revenue from participation in frequency regulation and potentially other markets. So I would hope that there is a baseline calculation, or I'm thinking of a baseline calculation that would basically make sure that at the end of the month there's no disadvantage to being part of that portfolio system. It's not a trivial problem. It's a difficult problem. Thank you. Yeah. But we're at the beginning of this research. Thank you, Pedro.
Some people in Malaga is intend trying to make a question. So, José Antonio, let's see if we are able to solve the delay problem, because they are watching you through YouTube with just 30-second delay, but now with Skype they are listening in real time to us. So there's a confusion of audio and video and everything else. This is new for us, so sorry for that. But somebody in Malaga, José Antonio, it's true. Can you? I've had microphone close to the computer, so hopefully everybody in the room can hear you now. José Antonio? José Antonio? Maybe he needs 30 seconds for you to code and compress and everything else to squeeze everything. José Antonio?
Yes, I'm here. I'm online.
Okay.
Thank you, Antonio. Thank you, Gregor, for a very nice talk. I would like to open the floor here to the audience here in Malaga, and Manuel will ask you a question. Please.
Okay, Manuel, go on.
If there is any...
Sorry, you, please go close to the computer. We cannot hear you.
Can you listen to me?
Yeah, right now, perfect.
Okay, thank you. Firstly, I would like to know if there is any practical example of multi-building optimization in the worldwide. And secondly, I asked if we can implement this idea in a whole small city, taking into account industries, electric vehicles charging, houses, and so on. Thank you.
Thank you.
Thank you, Manuel.
So the first question that was raised in Malaga was, are there practical examples? We have practical examples for single building optimization, but we do not yet, and that means single building optimization to respond to day-ahead energy and day-ahead energy markets. We have single building optimization with respect to frequency regulation. However, what we have done with this work laid the groundwork for the next steps to achieve a practical implementation. We have the optimization system that I described today is basically the same optimization system that is used for real-time optimal control of single buildings, but we have not yet been able to find two building owners in the same city or even in two different cities that would volunteer to simultaneously be considered in an aggregated portfolio. So that is something that we don't have a practical example for. So the results you saw today were just published in the journal Energy, and and we basically are hoping for field implementation of this coming soon. The second question is it possible to consider this optimization stretching an entire community, a small city, with other loads like electric vehicle charging? And the answer is yes. Everything we've done and I've shown today pertains to not just building schedules, but also it could involve optimal charging and discharging of other forms of storage. Among them, vehicle electric storage could be charged as well. So the short answer is theoretically we have everything in place to aggregate a small community or selected building out of a city plus electric charging stations to come up with a portfolio that could be in the same city or distributed, but we don't have yet the practical implementation examples.
Okay, so perhaps Gregor has visited already Malaga, but perhaps Professor Aguado is willing to show Gregor HENZE the smart city area in Malaga. Hopefully you will meet in the future.
Oh, I hope so.
So he said he hopes so. So I don't know. It's probably too late. So I don't know if there is room for any other question.
I'm here.
Running short of time.
They're not yet sleeping.
One final question if you want, but the last one. Here locally. No more questions. Okay, you have been interacting with them throughout the class, so I hope maybe it's enough. Okay, Gregor, thank you very much.
Thank you very much. Thanks to all of you.